Hello, this is a quick video about Norton and Thevenin transforms. So what we have here is a resistor and a voltage source, and here we have a current source and a resistor. And these circuits have the same properties. They have the same current I going through them, it's V over R equals I, and they have the same voltage across the resistor. Voltage across the resistor equals IR, and over here the voltage across the resistor is set by V. V equals IR. All of these are the same across both circuits. Resistance is the same. That voltage across R is the same as V, and I is the same. I from this current source is the same as I here. In these circuits, ignoring this bit for the time being, we have a voltage and a resistor, a current and a resistance in exactly the same way. These are in series, these are in parallel. This symbol I've just made up is a representative of some other bit of circuit which is looking into these two nodes here, these two terminals. These big dots represent terminals to external things, and this is the external thing that's attached to these two circuits. Now if this external thing puts a load on this circuit, it will notice a change in voltage, and the same will happen here. If this puts a load on this circuit, it will notice a change in voltage, and it will be the same change in voltage. If this circuit here puts another voltage on the output and forces current into here, it will notice the same current will flow in this circuit and in this circuit. So to all outside observers, this V and R circuit in series is equivalent to this current source and resistance in parallel, and that is the key to Norton and Thevenin transformation. This is a Thevenin circuit and this is a Norton circuit, and what they can be useful for is finding impedances and finding circuit properties of a black box. We can say that this black box, some sort of circuit which has terminals coming out of it. We don't know what's inside it exactly, but we can say, well, it looks like a voltage source in series with a resistance. We can say it looks like a current source in parallel with a resistance. And these are equivalent. These can be made identical from an external point of view. So we could use Norton and Thevenin transformation to solve circuits, to simplify parts of circuits. Say we had this circuit. Say we had a voltage source series with a resistance, and then two resistances, go on then, and then a current source in parallel with a resistance attached to an and then say another resistance, and let's say another voltage source like that. And we can use Norton-Thevenin transformation to turn this circuit into a simple circuit according to an observer connecting to these nodes. Let's say we had a resistor here. Let's label these R2, R1, R3, R4, RL for load, V2, I1, V1. We could take R1 and R2, they're in series, add those together, so then we could turn that bit of the circuit into a voltage source in series with a single resistance, R1 plus R2, that's V1, and then we could turn that bit of the circuit into something else. We could turn that bit of the circuit into a Norton circuit. We can do a Thevenin to Norton transformation, and we could turn this into V1 over R1 plus R2. That's the name of this current source. That's what this current source is outputting, and that's in parallel with a resistor called R1 plus R2. That's the value of that resistor. And then here we've got another I1, and that's got its own resistance, R3, and then there's R4, there's R4, and V2, and then RL. Because these are now in series, in parallel, we can do things like adding together these current sources. So the current contribution to these two equivalent, as we look at this end, we can then turn this into another circuit. Let's go up this way, and let's make this. So we've got this V1 over R1 plus R2 plus I1. That's what the name of this is. That's in parallel with a single resistor, which is R1 plus R2 in parallel with /R3. And then we've got R4 and V2, and then RL. And this is a Norton, and then we can turn that into a Thevenin circuit. So let's go this way. Let's use all the paper in a weird way, and we can turn that into a Thevenin circuit. So the current, the voltage developed across here. The basic principle is, it doesn't matter what's on the output here. It doesn't matter what this is or what this is. These two parts of the circuit are equivalent. So we're moving along, turning these into their equivalent parts, and then combining up the other things that end up in series or parallel. So this current source will turn into a voltage, because I times R equals V. So therefore this voltage here is going to need a really long equation, so I'm not going to write it here. Push that up a little more. I'm going to write the equation for this here. This is V N for nu. So Vn equals, using this current here, so V1 over R1 plus R2 plus I1, all multiplied by R1 plus R2 in parallel with R3, like that. So that's an equation for Vn. This is a voltage source Vn, and that is in parallel with R1 plus R2, in series with, sorry, R1 plus R2, parallel with R3, R4, V2, RL. So this circuit's now a hell of a lot more simple than this circuit here. Yes, our equations are getting longer and longer, but the circuit itself is getting simpler and simpler. So when we want to work out this current here, we'll end up with a circuit that looks like this, but with a resistance here, or maybe one like this with a resistance here. So with a circuit like this, you could see that if a resistor was here and a resistor was here, different resistances, we'd get a potential divider. We'd use a standard potential divider equation to calculate the voltage here, if that's what we wanted to find, the voltage across RL. So using these equations, we can further collapse this up. All we need to do is add Vn to V2 and put put this, add this and this, and we get our simple Thevenin equivalence. Let's do that now. So let's do that. Let's do that down here. So then we get RL, and this will be 1 plus R2 parallel with R3 plus R4. So break that off, and this here will be, well, V1 for R1 plus R2 plus I1 plus R2 in parallel with R3. If you've got a suitable fancy calculator, you could just put all of these numbers, because they would be numbers if we were finding the answer to a problem, plus V2, and that's what that is there. And then you could use the potential divider equation. Let's write it out in this space here. So VRL would be equal to the input voltage, which would be V1 over R1 plus R2 plus I1 R1 plus R2 in parallel with R3 plus V2 that's the input voltage, and the and multiply that out by the what we want to find, RL, divide that by the sum of the two impedances, which would be RL plus R1 plus R2 in parallel with R3 plus R4. And that looks like it. I don't think I've forgotten. Have I forgotten R4? Nope, I haven't forgotten R4. That was added in here. R4 was added to that. So that should be there. And input voltage does not depend on R4. It's that plus that. Yep, that's right. Yeah. So there we go. We've taken this weirdly complicated circuit, found an equation for it. If we had the numbers for this, we could put this straight in on an advanced calculator. And that's one way of using Norton Thevenin transformation to solve a problem like this. This might be especially suited for it. Yeah, I hope you learned something. Thank you for watching. Goodbye.